All right, so in Unit 5, you learned all sorts of indefinite integral rules and how to integrate them, the functions. So in Unit 6, all the topics are going to be related to definite integrals. So first, let's make some connections. Before, what we had was we talked about derivatives, and we referred to them as we could find a derivative using the slope of the tangent line to a function, okay? And so positive slopes meant a positive derivative, negative tangent slopes to the function meant a negative derivative. So for integrals, we're going to do the same idea. So for area under a curve, we are going to define that the area between the function f of x, the x-axis, and two vertical lines like x equals a and x equals b, we're going to refer to that area as the definite integral. So typically you've seen the integral symbol next to a function, a derivative function. Now we're going to add what are called limits of integration. So this is the upper limit of integration and the lower limit of integration. Now, lower limit. Even though we use the word limit, this does not refer to the ideas that we used in Unit 1 and 2 for those limits, okay? So these are really like your boundaries. Remember, these are actually x values. We don't write x equals a and x equals b, but that's what's understood by the notation, okay? So the idea on a graph is if we would read this as the definite integral of f of x between x equals a and x equals b. So note that the definite integral sign, it is the same as the indefinite integral sign, except definite integrals have limits. So obviously we're going to learn some rules about those limits throughout this unit, okay? So there is an intentional connection between the process of finding an area under a curve and taking integrals or antiderivatives, all right? So when you see a definite integral right here, you should start to think of, oh, that's area under a curve. Okay, just like when you saw derivative, you think, oh, slope of the tangent line, all right? But you want to be careful. Areas, you've learned in math, areas are always positive. Definite integrals can be both positive and negative. So what I want you to do is we're going to have a concept called signed area under a curve. That's really important, okay? So now we're going to do some rules. So when a is less than b, remember a and b are the limits of integration or the boundary lines of the area, then the integral is being analyzed from left to right. Like, let's take this picture up here. See how a, this could be like 2, and b, this could be like 5. And so 2 is smaller than 5, so that's going from left to right. So that means that you're going forward, and that's how we read a graph. So that should be normal to you, okay? So if the function is above the x-axis, that area, and your limits are going forward, then you're going to get a positive number, okay? Now, let's think about something else. What if we switched and we said, what if a is bigger than b? Well, if a is bigger than b, like a could be 5, and b could be 3, it would look like this from 5 to 3. And so this might not look unusual to you, but it will soon, okay? You always want it to be the lower limit, which means smaller, and the upper limit should be bigger. You can't just change these. So if you notice that you have an integral value that's written this way, where a is larger than b, it means you're going from right to left, and that's backwards. So what that means is that you are going to get a negative integral value, all right? Now, there's other ways we can talk about the limits going forward in order or backwards, but we can also talk about area being above the x-axis or below the x-axis. So there's two different kind of forces at play. So think about that. If we had a graph, and let's say this is A and B, if we had our curve was under the axis and we want to integrate, then when we integrate, since our area is under the curve, we are going to also end up with a negative integral value, okay? Because we're using the area to get the value, and then we're interpreting it using the signed area to get the actual value of the answer, the sign of the answer, basically. So if we wanted to go on the same graph, if we went from B to A, there's two different things at play. One, we're going backwards. So I don't think of it as negative. I think of it as the opposite. And our area is under the graph, so our integral value is going to be negative. So you have a backwards negative and an area that's under the graph, which is negative. So a negative and a negative will result in a positive integral value. Okay, so see how there's two different things to be looking for: above and below the axis, and your limits forward or backwards. All right, and so that's what this chart summarizes. I don't like to memorize charts because I just think if you work through it logically, it's easier to remember. So definite integrals, the biggest interpretation is to use signed areas to get the value, okay? All right, so here's some rules, and these rules should look very similar to our derivative rules because they apply, all right? So if we notice our limits, if we go from like 5 to 5, that means on the graph we didn't go anywhere, so we didn't accumulate any area. So our integral value should be 0. This will be used to kind of prove other integral values, but it's not used very often, just like we didn't do it very often in the derivative. We've already talked about if we want to have our limits, because typically if you switch the limits here, it's going to be the opposite. Okay? So I don't want to say positive or negative, I just say opposite. You negate the integral value, whatever that is, depending on the graph. A constant being multiplied, like if you had 5 times x squared, because that constant is being multiplied, we can factor that out, just like we did with the derivative. Okay? If two functions are being added or subtracted, eventually we're going to be doing integrals by hand, so we can actually integrate them separately. Or this applies to areas. We can split them up as long as they're connected and add or subtract their respective integral values. Okay? And then the last one, I like to draw a little picture. Let's say A, B to C. So let's say if we take from A to B, and let's just say it's this area, and from B to C, let's take this area, then what happens is we can actually take, as long as they're joined together from A to B and B to C, see we don't have any gaps in the x values, we can add the entire thing all in one step if possible. Okay, and this is kind of like the transitive property of integrals. We just don't call it that. So let's do some examples. Now, these, it looks like a lot. This could be a multiple choice or free response question. I'd like to go through all the different scenarios from A through T using this graph. Okay? And we're honestly not going to learn a quicker way to do this. There's really only one way to do it. So this is how we start. Okay, on part A, so we want to go from 4 to 4. So here's 4, and it says, hey, start here and end there. Well, we didn't amass any area. From 0 to 1, so I'm looking at right here, we want to find that area, which these are nice square units. And notice these are geometric shapes because that's the area formulas that you've learned in geometry. They tell you it's formed by lines, and they're telling you it's a semicircle. Okay, so we get length times height. It's a rectangle, and I'm going to write that area there. You'll see why soon. We're above the axis. Our limits went forward, so we keep the same signed area. From 1 to 3, so we're looking at this triangle region right here. It's a triangle, so 1/2. The base is 2. The height is 2, and so 1/2 of 4 is 2. We're above, the area is above, and our limits go forward. So I'm going to write this here as well. Part D, we want from 0 to 3. So from 0 to 3, since those two areas are connected, we can add them together. Okay. On part E, we want to go from 3 to 6. And so notice our area is under the x-axis. So I automatically know it's going to be a negative value. And it's one triangle. I can do it all together. So 1/2, the base is 1, 2, 3, times the height is 1. So I get 1.5, and it's under, so I'm going to write negative 1.5. Trying to make sure I can read that. So negative 1.5. Okay. Now, notice on F, you really have to start paying attention to your limits. My bigger x value is in the bottom, and it's not supposed to be. So really, I can take the opposite of 3 to 6. So we found 3 to 6 in the last one. So this is going to be positive 1.5. No, you don't have to write the plus there. I just want to emphasize that it is the opposite. Okay? And so on part G, we want to go from x equals 0 to x equals 6. So we're going to use those signed areas. So it really is 4 minus 1.5. Once again, you don't have to show your thinking there. This would be like right or wrong. On part H, they want to go from 6 to 10. So that is a semicircle. So 1/2 pi r squared. The radius is 2. So 4, 1/2 of 4 is 2, so 2 pi. And you just want to leave this as 2 pi, no decimals. Above the axis, so positive integral value. Part I, they changed those limits, so take the opposite. And then part J says go from 0 all the way to 10. I'm going to write that in there. So I need to add these all together. So we get 4 minus 1.5 is 2.5 plus 2 pi. Okay, and so notice when you just see that integral value, you cannot actually tell that any of those areas were under the x-axis because our overall integral value would be positive. Okay, so when you're given integral values, you can't assume things about the original function. Keep that in mind. Part K, notice our limits are reversed, so that takes the opposite of our entire value. So we've got negative this whole answer, which really, I don't like to leave parentheses in an answer, would give us that. All right, on L, our limits, we do go from -1 to 0. Now, you have two choices. This, if you do it as one shape, is really a trapezoid. Remember, like this is my base, this is my base, this is my height. So it's like a sideways trapezoid. So as a review for a trapezoid, when this is my height, base 1 and base 2, that's an h there, you get h over 2, base 1 plus base 2, if you want to do a trapezoid altogether. Your other choice is to split this up, and you've got a triangle on top and a rectangle on bottom, okay? So it's really up to you. I'm a big fan of trapezoids. So my height is 1 over 2. My first base is 1, 2 long, and my bottom base is 1, 2, 3, 4. Our area is above the x-axis. We went forward, so it's going to be positive. So 1/2 of 6 is 3. Part M, we want to go from -3 to 0. I'm going to write this here. Let's erase. Okay, so we get 3, -3 to 0, so -3 to 0. I've already done this part. You could split these up. I mean, there's lots of different choices. I've got a triangle here. I could have another triangle. So start getting comfortable with what you want. I am going to have to split this up into triangle, and then I'm going to keep this as a trapezoid. But if you don't like the trapezoid, I could do a triangle here, split this up into a rectangle right there. Lots of options, okay? So 1/2, my base is 1, and my height is 1, 2, 3, 4, 5. So 2.5. This trapezoid, its height is 1 over 2. This base is 1, 2, 3, 4, plus 1, 2, 3, 4, 5, 6. So 1/2 of 10 is 5. Okay? So all together from -3 to 0, we've got 8, 9, 10 and a half. Above the axis, so we're positive. I'm going to amend this. I'm not sure what I was doing. This height is 1, 2, 3, 4, 5, 6. So 1/2 of 6 is 3. I am not sure why I counted that way. Where we go? 3. So that makes this 11. Okay. Part N, you'll have to notice that they reverse the limit. So we're going to take the opposite of what we did in M, because we would be going backwards. Okay. For part O, from -4 to -3, that's in the right order, from smaller to larger. Our area is under the axis, so we're going to get a negative integral value. So 1/2, our base is 1, and our height is 1, so we get 1/2. You can write a decimal if you like. So from -4 to 0, this was -1/2. It's really tiny. We had 11, take off that half, is 10.5. Overall, we had more positive area than negative area, so that's why our integral value, it's like the net area. That's a concept we'll be exploring. All right, part Q, we want to go from -4 all the way to +10. So I know from -4 to 0, we have 10.5. I'm just going to make a little note. And then we're going to add 4, take off 1.5, and then add 2 pi. And you could do this, you don't have to show any work. So we would end up with, what, 2.5 plus 10.5 is 13 plus 2 pi. Okay. Now, notice the difference between R and S. And they are different. They mean different things. And depending on the graph, sometimes you get the same answer. You're lucky. Sometimes you're not. But let's go through what they mean. So on part R, let's see if you can tell what the difference is. All right. I know it's hard to pause on a video, but what this means, since the absolute value bars are on the outside, it means do the inside first, which is part Q, and then make your entire answer positive, okay? Then we'll put answer, make positive. So it is what we did on part Q, and 13 plus 2 pi is already a positive answer. So by luck, if you didn't even know what the absolute value bars mean, on this graph, you would have gotten lucky and got the same answer, okay? That doesn't always happen. Let's say if both of these were negative or one of these was negative, you would have to change some of the signs in order for your overall answer to be equivalent, but just be a positive value, okay? That's the concept. On part S, when the absolute value bars are inside and around the function, inside the integral, and around the function, what that means is to make all signed areas positive, then add them up, okay? So it's a very different concept. So on this problem, all of the positive areas are fine, but this -1/2 and this positive 1.5, we're going to make them positive when we add them all up, okay? So that's the idea. So we would have 3 plus 5 plus 3 plus 2 plus 2. What's that? 8, 9, 10, 11, 12, 13, 14, 15. These two negative areas are -2, but I'm going to make them positive. And then I'm also going to add that 2 pi. This is what you would be doing in your head. So altogether we get 17 plus 2 pi. Okay. On part T, there's no absolute value. We have this -2 that's being multiplied, and our limits are backwards. So really, this negative, I can adjust that by taking it out, and it will switch my limits for me. Okay? So then we can factor out the 2, positive 2. So we want to go from -1 to +1. So -1 to +1. So we've got 5. And we multiply those together. All right, so on section 2, we're not going to be given any areas or any graphs. But remember, we are going to be given some integral values. And these are the overall net signed areas. So like right here, from -2 to 5, it doesn't mean that all of the areas are above the axis. It means overall, there are 18 more units above the x-axis than below. Okay, so I think of integrals as net area. Same thing with g, h, and then notice our limits are a little bit different. Okay. So on our first example, we're adding two functions together, and so really we can add these separately because they're being added. So by substitution, I know that this is 18, and -2 to 5 of g, that's 5. So we add them up, and it's 23. Okay. On the second one, there's a 4 that's being multiplied. We can factor that out, but I also notice that my limits are backwards. So if I factor out a -4, I can switch those limits. And then by substitution, we get -20 integral value. All right, the next one is often missed if you just are trying this on your own. But this is saying take our function f and subtract 6 on the whole from this entire integral from x equals -2 to x equals 5. It doesn't mean, notice how that -6, it doesn't mean just to take your integral value and subtract 6. That's the common error. So because these are being subtracted, remember we can do the integrals separately. So we're going to. So by substitution, we know this is 18. Now let's think about a graph. Okay, since I'm not given any information about 6, we have to think of what does that really mean? So I'll show you once, and then you probably can think of shortcuts after this. So it means we want to go from x equals -2 to x equals 5 of this graph, which is 6. So that's a horizontal line. We could also use -6, but I'm just going to subtract, okay? So that means we can find that integral value by using the signed area. This is a rectangle, so length times width means we're 7 wide, we're 6 tall, and so that area is 42. So that integral value, I would have 18 minus 42. Okay, which... let's just double check. I always make little errors, so -24. Okay, so one way to find an definite integral value is for you to make the graph, and especially if it's a geometric area, and use its signed area. Okay. All right, number 7 is it's kind of going to mix integrals with use of definite integrals with area and use substitution. So we don't know anything about x minus 2. What that x minus 2 is, if you remember your graphing rules, is it's a horizontal translation. So it takes all of the y values and the x values, the ordered pairs on the graph of h, and it actually moves it to the right 2 units. Okay, we don't know what these graphs look like, but what we can do is kind of combine the idea of u substitution. So we're going to say, what if we let u equal x minus 2? Okay, and so you don't even have to remember that that's a transformation because u substitution takes care of that. So du equals 1 dx. And so by substitution, I would have h of u du, because that's just dx, except remember, these are x limits. And so we can't have an integral limit with a different integral variable. So we also want to change these limits into u limits. And so we do that by substitution. So if x equals 7, that means 7 minus 2, u equals 5. And if x equals 0, 0 minus 2, okay. Now, we're going to introduce an idea that it kind of takes a little bit for you to wrap your mind around, and until we learn more integral rules, some of you might just have to blindly trust me. But we decided to use the substitution, and so we did that whole transformation, and these two functions are equivalent signed areas, okay? Because we changed the limits, we changed where its like starting point is. Now, I really could change these to any letter. H of negative 2, if I had other variables, I could change these to anything I want. So these are kind of called dummy variables. Now, as long as your limits are the same variable as your function, then they always work, okay? That's why I had to change my x limits because I wasn't keeping my x here. So even though these are u limits and a u function, all of these concepts are the same. Like I could say, if I defined another variable as a, these could be a limits. And I could change this into a, dA. As long as they all match, they really will give you equivalent integral values. We're just moving them left and right. And like for time, we do this as well. We did it with derivatives. We would just say, oh, let's not use x, let's use t. If t bothers you, change it back to x. We're not just cheating, okay? So let's erase this so I can see future problems. And so even though these are in terms of u, these values will still be equivalent. Okay, and that takes a little bit of trust and conceptualizing for you to start to believe. So right here, I would get negative 11. Okay, so this is just the dummy x variable with x limits. It really will be equivalent to h of u because this is a variable. It's still the same function. Okay, I really could have let this be like x equals x minus 2. It's just that gets confusing. That's why we set up this dummy variable. And I don't know who picked u to begin with. We just picked it. We don't want to pick y. We usually don't pick a and b. So we just, u really hasn't stood for much else in math. Okay. All right, let's look at my next one. We want to go from 5 to 8. So what I notice is we don't have anything that goes from 5 to 8. And I don't need to change this because it's not a transformation of the function. Okay. But let's look back at the f function and what we know. So I like to make a little number line, and I'm going to do it up here. So what I know, I'm going to make just a number line. We could do this on a graph too. If I go from negative 2 to 5, I know that that overall value is 18. Okay? We can act like it's above. It doesn't matter. And I also know that from negative 2 to 8, we know that overall sign value is going to be 0. And it's like, wait, hold on. So obviously we can't be all above because I can't have an integral value of 0. So what had to happen? Well, something had to happen from 5 to 8 because I know the total is 0. Well, this is just an equation. You can think of this as 18 plus what has to give me 0. And you're thinking, oh, well, it has to be negative 18. So even if this was all above, this had to be all below in order to make that total integral value true. Okay, so that's kind of like that transitive property, but in a different order. So what I know is that from 5 to 8 of f of x, it had to be negative 18, using that idea. Okay. All right, the next one kind of combines a few ideas. So I'm going to integrate these separately. Notice my limits stay the same. And on this one is that transformation idea. So I'm going to do my change of variables. So I get, I'm going to make this smaller because there you go. I like to see both. I get f of u du. And then these are x limits. So if x is 1, 1 minus 3. And if x is 8, 8 minus 3. Okay. And then this one I need to use my area. So I'm going to go from 1 to 8 of y equals 3. And if you can do this in your head, that's fine. So that area would be length times width. And so I get 21. This integral value, I keep moving it and I want to use it, from negative 2 to 5 of f is 18. So I get 39. All right, my next one, you have some choices. My limits are backwards, so I can change them, or I can work with them each separately. I'm just going to go ahead and change them. So if I factor out a negative or multiply by a negative on the inside, then I can change those limits. And I like to do that before I even do the problem. And that would make that a plus. And then we still can integrate these separately. So on this one, I have a graph, and I'm just going to use y equals negative 1 from 5 to 8. So length is 3, the height is negative 1, so that integral value is negative 3. And that should make sense since we're under the x-axis. From 5 to 8, didn't we say that was negative 18? Yep, of f. So we get negative 21 altogether. All right, my last one. Now, the way absolute value works is geometric area. We need to figure out that shape. So x minus 2, we can find out two different ways. I can take that line, which is up 2, and it's a line with a slope of 1. So I'm going to go up 1 over 1, down 1, down 1, down 1, and it would be a line. So if we want the absolute value, wherever you had a negative y value, it bounced that up. So that's not there. Okay, that's one way to do absolute value, especially if it's not a line. So if you have curves, you'll need to use that concept. Or I could find the vertex. So set this equal to 0, and that will help you find where it touches the x-axis. So subtract 2, so at x equals negative 2, I know I would have that anchor. And then you can just make a table of values. Plug in negative 3. I mean, there's so many choices for graphing. Negative 3 plus 2 is negative 1. The absolute value is positive 1. So that's at 1. At negative 1, I get 1. At 0, I get 2. And I want to go to 3. So I'm going to go 1, 2, 3. I don't care about 1 and 2. So 3 plus 2 is 5. So we have, oh, that's a terrible graph. Let's go higher. That's a line, straight line. Okay. So to evaluate the integral, we're going to use the signed area. So we're really going to go from negative 3 to negative 2. We need to find that triangle area. And then we can add this one last triangle area from negative 2 all the way to 3. That's kind of the concepts we're doing. Okay. So I get 1/2. That base is 1. The height was also 1. So we get 0.5 plus 1/2. This base is 1, 2, 3, 4, 5 times its height was also 5. So 25, half of that is 12.5. So we get 13. And for absolute value, using the graph is going to be your go-to strategy. So on your assignment, I give you very similar ideas to practice. I did throw this question in there. I think you should be okay though. All right, so go ahead and give those a try and see how you do.